Welcome to the Curious Voyager. It's lovely to have you here, wherever here happens to be tonight. Maybe you're under a heavy blanket with the lamp still glowing in the corner. Maybe you're on a train, or a couch, or lying flat in the dark with your eyes already half closed. Wherever you are, settle in. You don't have to do anything now except breathe a little slower and let the world get quiet around you.
And while you're settling, I'd love to know, where in the world are you listening from tonight? What time is it in your corner of the night? If you feel like it, leave a little note before you drift off, because honestly, it's one of my favorite things. Imagining all these scattered lamps and dark rooms, all of us awake at the same odd hour, thinking about the same strange and beautiful thing.
And if you've enjoyed these slow journeys before, a gentle like or a subscribe really does help this sleepy little channel keep going. Small creators like me rely on it more than you'd think. And to those of you already here, already part of this, thank you. Truly, you make the quiet feel less lonely. Quiet feel. Now, here's my promise to you for the night. We're going to move slowly. Very slowly. There's no rush at all, no test at the end, nothing you have to hold on to. If you drift off somewhere in the middle, that's perfectly fine. That's sort of the point. The ideas will still be here when you wake. I'll try not to make any of this so interesting that it keeps you up. But if it does, well, at least you'll have learned something lovely. A fair trade, I think. So let me tell you about a cup of liquid that empties itself, not by evaporating, not by leaking through a crack in the bottom. I mean a sealed, ordinary, smooth-walled little cup, sitting perfectly still on a bench doing nothing at all. And yet when you come back to check on it, it's empty. The liquid is gone. And if you'd been patient enough and watched closely enough, you'd have seen the strangest thing. You'd have seen the liquid climb up the inside wall, all on its own.
Against gravity, up to the rim, over the top, and then down the outside, where it gathers at the very bottom of the cup and falls away, drop by drop, into nothing. A liquid that climbs out of its own container.
Just sit with that picture for a moment, because it's the whole story, really. And we'll be returning to it again and again tonight, turning it over slowly like a smooth stone in the hand. A cup that drinks its way out of itself. A puddle that decides quietly and without any fuss to leave.
And I want to tell you up front, this is real. This isn't a thought experiment or a clever animation or some legend that scientists half believe. You can do this in a cryogenics lab with the right equipment and a great deal of cold. You can pour this liquid into a little vessel and watch it crawl out every single time as reliably as water runs downhill. It's been done thousands of times. It is not magic. It is not a trick.
It is one of the most thoroughly understood things in all of physics, and it is still one of the strangest. The liquid is helium, and not just any helium, helium chilled to within a whisker of the coldest temperature that the universe will allow. We'll get there slowly, you and I. We'll take the long road down through the cold, 1 degree at a time, because the real wonder isn't just that it happens, it's why. And the why is, I think, more beautiful than any of the myths people tell about it. Because here's the thing you'll hear if you ask around. People will tell you this liquid defies gravity. They'll say it breaks the laws of physics. They'll say it knows how to escape, as though the cup were holding a small, clever animal that was simply waiting for its moment. And I understand why they say it. When you watch it for the first time, that's exactly what it feels like. It feels like the liquid wants out. It feels like a rule has been broken somewhere, quietly behind the scenes, but none of that is true. The liquid doesn't defy gravity. Watch it carefully, and you'll see it falls off the bottom of the cup, dropping under gravity just like anything else, perfectly obedient. It doesn't break any law. And nobody is baffled by it, not anymore, not for a long time now. It was explained beautifully decades ago. So if it isn't fighting gravity and nothing is pulling it up the wall, then why on earth does it climb? That's the question we're going to circle tonight. And I'll plant the answer right here at the start, like a little seed, even though it won't make full sense yet. Hold on to these words as you drift. It climbs not because something is pulling it up. It climbs because nothing is holding it back. That's the whole secret, really. The whole impossible seeming business comes down to a single absence, something that every other liquid has, and this one simply doesn't. We'll find out what that missing thing is. We'll find out why it goes missing. And once you understand that one vanishing, every other wonder, the climbing film, the fountain that runs on a flashlight, the flow that never stops, they all fall into place, one after another, like a row of soft dominoes. They're all the same single fact, seen from different angles. But to get there, we have to go cold, colder than you've ever imagined cold could go. So let's begin our descent gently, no rush. Let me set the scene, because every good story has a doorway, and the doorway to this one opens in a city in the Netherlands, in a laboratory, more than 100 years ago. The city is Leiden. The man is named Heike Kamerling Onnes. And the date, I love that we even know the date this precisely, is the 10th of July, 1908. Now, to understand what Onnes did, you have to understand the obsession he was chasing, because it was a kind of race, slow and quiet and decades long, and it was a race toward the cold. By the late 1800s, scientists had figured out something wonderful and a little upsetting, that the air around us, the very air you're breathing right now, isn't really a permanent, unchangeable thing. Squeeze it hard enough and chill it down far enough, and it turns into a liquid. Air becomes a pale blue fluid you can pour. Oxygen, nitrogen, gases we think of as the emptiest, most untouchable things in the world. They all surrender, eventually, if you make them cold enough. They give up being gas, and they become liquid, sloshing in a flask. One by one, the gases fell. Chlorine, carbon dioxide, oxygen, nitrogen, hydrogen, each one liquefied at colder and colder temperatures, each one a little victory in this long campaign against the heat. And there was a phrase for the stubborn last holdouts, the gases that refused to liquefy no matter what anyone tried. They were called the permanent gases. Permanent because they seemed like they'd stay gas forever, immune to any cold a laboratory could throw at them. And the most stubborn of all, the very last one standing, was helium. Helium is a peculiar little element. It's the lightest of the noble gases, those aloof, standoffish elements that don't like to react with anything, that keep entirely to themselves. A helium atom is small and shy and almost weightless, and it does not want to be a liquid. It does not want to be anything but a free, flying gas, racing around at enormous speeds, bouncing off everything and bonding with nothing. To pin it down, to slow those frantic little atoms enough that they'd huddle together into a liquid, you had to go colder than anyone had ever gone. And Onnes, in his laboratory in Leiden, was the one who finally did it. I want you to imagine that lab for a moment, because I find it soothing somehow. Picture the brass and the glass, the tangle of tubes, the great pumps breathing in the corner, the careful men in their high collars moving slowly and deliberately, because everything they were doing was delicate beyond words. Onnes ran his laboratory almost like a workshop, with skilled glassblowers and instrument makers, all of it built around one patient goal: to make things cold, and then colder still, and to see what the world does when you take nearly all of its warmth away. Cold, you see, is just slowness. That's a gentle way to hold it in your mind as you lie there. Heat is motion, atoms jiggling, racing, vibrating, bumping into one another in a ceaseless, restless dance. The hotter something is, the more frantic that dance. And cold is simply that dance slowing down. To cool something is to ask all its tiny moving pieces to please gradually be still. And the coldest cold imaginable, at the very bottom, the temperature physicists call absolute zero, is the place where all that jiggling would in principle come almost completely to rest. The great stillness, the floor beneath all temperatures below which there is no lower. We measure temperature in those cold realms using a scale that starts right there at that floor, at absolute zero. We call the units Kelvin, and on that scale, 0 Kelvin is the bottom of everything. Room temperature, where you probably are right now, is around 293 Kelvin. Water freezes at 273, and the gases all kept giving up the ghost at lower and lower Kelvin numbers as the years went by. ONS had to get all the way down to about 4 Kelvin, 4 degrees above the absolute bottom of cold, 4 degrees above the stillest stillness there is. And on that July day, in 1908, after years of patient work, after building cooling machines that nested inside one another like a set of Russian dolls, each one chilling the next a little further down, he did it. The helium gas in his apparatus surrendered at last. It became a liquid, a clear, almost invisible liquid, lighter and thinner than water, boiling away in its little glass vessel at a temperature of roughly 4.2 Kelvin, around minus 269 degrees Celsius, so cold that the number almost loses meaning, so cold that it sits less than 5 degrees above the absolute end of cold itself. Helium, the last permanent gas, was permanent no more. It was a triumph, and the world knew it. 5 years later, in 1913, ON was given the Nobel Prize in Physics for it, for opening the door to that frozen country, for being the first human being to hold liquid helium in a flask and watch it shiver and boil. He had reached a place no one had been, and what he didn't fully realize, what nobody realized yet, was that he'd only arrived at the front porch. The truly strange country lay further in, further down, colder still. But before we descend any further, and we will slowly in a moment, I want to linger on this liquid helium itself, because even sitting there at 4.2 Kelvin, boiling away like an ordinary cold liquid, helium was already hiding a secret that should have raised more eyebrows than it did. A secret it carries all the way down to the very bottom. Here it is. And it's lovely, I think, in how quietly impossible it sounds. Helium does not freeze. Now, I don't mean it's hard to freeze. I don't mean you have to work at it. I mean that liquid helium left to itself will not become a solid no matter how cold you make it. You can chill it down toward absolute zero, down past 4 Kelvin, past 1 Kelvin, down and down toward that final floor of all temperature. And it stays a liquid the whole way. Every other substance in the universe, if you take enough heat away, will eventually freeze solid. Water becomes ice. Air becomes a kind of frost. Even hydrogen, even the gases, surrender into solids if you go cold enough. They all, in the end, lock into place. They stop sloshing and they hold still and they become crystal, but not helium. Take it as cold as it can possibly go, all the way to the very edge of absolute zero under its own ordinary pressure, and it remains liquid, still flowing, still soft, still refusing to settle. If you actually want to force liquid helium to freeze, and you can, but you have to bully it. You have to squeeze it hard. You have to apply something like 25 atmospheres of pressure, 25 times the weight of all the air pressing down on you right now, crushing the helium together until it has no choice but to lock into a solid. Only under that enormous squeeze will it finally crystallize. left alone at the gentle pressure of its own vapor. It never, ever does. It is the one substance in all of nature that simply will not freeze on its own, the eternal liquid. And here's the part I find genuinely soothing to think about as you lie there, because it's the first whisper of the deep strangeness we're descending toward. Why? Why won't it freeze? What's stopping all those atoms, even at the very bottom of cold, from finally settling down and locking into a crystal like everything else does? The answer is something called zero-point motion, and it is one of the gentlest, oddest ideas in all of physics. Remember how I said cold is just slowness? That to cool something is to slow down its endless jiggling, and that absolute zero is where that jiggling would, in principle, stop? Well, it turns out that's not quite the whole truth, because the world, at its very smallest scale, plays by quantum rules. And one of those rules is that you can never, ever make a tiny particle hold perfectly still. Not even at absolute zero, not even in principle. There is always a little tremble left, a faint, irreducible quiver that can never be stilled, no matter how cold you make things. Think of it like this. Imagine trying to balance a marble at the very bottom of a smooth round bowl. In the ordinary everyday world, you could let the marble settle, and it would come to rest right at the lowest point, perfectly still. But in the quantum world, the marble is never allowed to be perfectly still at the bottom. It always has to keep trembling, just a little, forever. A faint, restless shimmer that can't be removed. That trembling, that unremovable bottom of the bowl quiver, is the zero-point motion. It's the motion that's left over even when you've taken away all the heat there is to take. Now, for most substances, this little quantum tremble is far too small to matter. The atoms are heavy enough and they pull on each other strongly enough that the tremble is just a tiny background fidget. The atoms lock into their crystal anyway, trembling faintly in place like people standing very still in the cold, but shivering just slightly. The shiver doesn't stop them from holding their positions. But helium is special. Helium atoms are extraordinarily light, among the lightest atoms there are, and they barely pull on each other at all. They're those shy, standoffish, noble atoms, remember, that don't like to bond with anything. So the forces trying to hold them in place are feeble, and the quantum tremble, the zero-point shimmer, is, by comparison, enormous. The atoms are jittering so much, even at absolute zero, that they simply cannot hold a fixed position in a crystal. Every time they try to settle into the rigid grid of a solid, that irreducible quantum quiver shakes them loose again. They're too restless, too light, too full of that bottomless shimmer to ever sit still. So they stay liquid forever. The atoms keep flowing past one another in a soft, endless, trembling dance, kept fluid not by warmth, there is no warmth left, but by the deep, quantum unwillingness of the world to ever let anything be perfectly, finally still.
Isn't that a tender thing to know? That down there at the very bottom of the cold, in a place colder than anywhere in nature, there's a little liquid that simply will not stop moving. Not because it's warm, not because anyone's stirring it, but because the universe, at its smallest scale, doesn't allow perfect stillness. There's always a tremble left, always a little motion that no cold can ever take away.
And that quantum trembling, that refusal to freeze, is your very first clue that helium down here is not playing by ordinary rules anymore. It's the first sign that we've wandered into a place where the everyday laws of liquids start to soften and bend into something new. Because a substance that won't freeze even at absolute zero is a substance where the quantum world isn't hidden away in the invisible realm of single atoms, the way it usually is. Here, the quantum world has grown large enough to see, large enough to pour into a cup, And that, my friend, is the whole reason this liquid does the impossible-seeming things we're going to watch it do. But I'm getting ahead of myself, and there's no need to rush. We've only just arrived at 4.2 Kelvin on Honors's bench in Leiden, watching that thin, clear liquid boil. We've learned that it won't freeze, and we've learned the gentle quantum reason why. That's plenty to hold for now, because the real threshold, the one true line we're descending toward, the place where everything changes all at once, is still below us. We haven't reached it yet. At 4.2 Kelvin, this liquid helium is strange, yes, but it still mostly behaves itself. It boils, it sloshes, it pours like a thin, cold, ordinary liquid. If you didn't know better, you might think it was nothing special and just very, very cold. But there is one temperature, just a couple of degrees lower than where we're standing now, just over 2 degrees above the coldest cold that can ever exist. And when this liquid crosses that one particular line, something happens that has no equal anywhere else in the everyday physical world. The boiling stops all at once. In an instant, the furiously bubbling liquid falls completely, eerily silent, and goes as still and smooth as glass, as though someone, somewhere, had quietly thrown a switch. And on the far side of that line, in the silence, the cup begins to climb. We'll cross that threshold together in a little while. We'll find out its exact temperature and the lovely reason for its strange name, and we'll meet the people who first stumbled into this silent country and didn't quite believe what they were seeing. There's a man in Moscow, and there are 2 men in Cambridge, and there's a story of a scientist who went home for a visit and wasn't allowed to leave. All of that is waiting for us, just below. But for now, just rest here with me at 4.2 Kelvin on the porch of the cold. Picture the thin, clear liquid in its glass, boiling softly, 100 years ago in a quiet laboratory in Leiden. Picture Ons leaning in to look at the thing no one had ever made before. He's reached a place no one has been, and he doesn't yet know, nobody knows yet, that just a little further down, the liquid he's made is going to start doing something that looks for all the world like a small miracle.
It isn't a miracle, we know that now. It's something better. It's the quantum world grown large enough to watch with your own eyes, climbing quietly up the side of a cup in a film a few hundred atoms thick. And it climbs, remember, not because anything pulls it up. It climbs because down there in the cold, there is suddenly nothing at all to hold it back.
So let's keep going down. Slowly. 1 degree at a time. The cold is patient, and so are we. And the strangest, softest country in all of physics is waiting for us, just below the silence. But before we go any lower, let me tell you about that little glass cup of liquid Ons was looking at, because everything strange that follows hangs on one quiet, almost unbelievable fact about it. This liquid will not freeze, no matter how cold you make it. You can take it down and down toward the very bottom of the temperature scale, toward absolute zero itself, and helium simply will not turn solid. It stays liquid all the way down. It is the only substance we know of that does this, the only one that refuses to ever become a solid under its own quiet pressure, no matter how deep into the cold you carry it. Now sit with that for a moment. Everything else freezes. Water becomes ice. Air, if you chill it far enough, becomes a pale blue liquid and then a solid. Every gas you can name, every liquid, every metal, give it a cold enough night and it will lock itself into a crystal, its atoms settling into neat, still rows like people finally lying down to sleep. That is what cold does. Cold is the great stiller. It takes the restless jitter out of everything and lets it settle. But not helium. Helium never settles. And here's the gentle reason why, and it's one of the loveliest ideas in all of this, so let it wash over you slowly. We tend to imagine that at absolute zero, the very coldest cold that can exist, everything would finally stop. All motion ceasing. Perfect stillness, a universe holding its breath. But that isn't quite how the quantum world works. Down at the bottom, the atoms still move, they still tremble, just a little. There's a faint, irreducible quiver built into the deepest nature of things that can never be taken away, no matter how much heat you remove. Physicists call it zero-point motion. The motion that remains when all other motion is gone. The shiver at the bottom of the world. For most substances, this little shiver doesn't matter much. Their atoms are heavy, and the forces pulling them together are strong, so even with that faint quantum tremble, they still lock into place when they get cold enough. The shiver is there, but it's drowned out like a whisper in a crowded room. The atoms settle anyway. But helium is the lightest of all the liquids. Its atoms are tiny, feather-light, and the forces that hold them to one another are barely there at all, the gentlest of pulls. And so for helium, that faint quantum shiver isn't a whisper in a crowded room. It's the loudest thing happening. The atoms are so light and the grip between them so soft that even at absolute zero, the trembling is strong enough to keep them from ever settling down. They jitter forever. They can't sit still long enough to build a crystal. The cold tells them to lie down and sleep, and they simply can't. They're too light, too restless, too alive with that bottom-of-the-world shiver. If you truly wanted to force helium to freeze, you couldn't do it with cold alone. You'd have to squeeze it. You'd have to press down on it with about 25 atmospheres of pressure, 25 times the weight of the whole sky pushing on it, just to crowd the atoms close enough that they'd finally hold still and become a solid. Without that pressure, without that enormous squeeze, helium stays liquid forever, all the way down to the coldest place that can be. It is, in a way, the one substance that never goes to sleep, no matter how long the night. I find something wonderfully comforting in that. The whole universe wants to settle, wants to still, wants to crystallize into quiet. And here is this one light, gentle thing that simply keeps moving softly, endlessly, refusing the great stillness. Hold that thought as you drift, and you don't have to do anything with it. Just let it be there. So that's the cup. That's the liquid. A clear, cold, restless thing that will not freeze, boiling softly in its glass, in a laboratory in the Netherlands a long, long time ago. Let me take you there, just for a moment, because it's a place worth resting in. The city is Leiden, in Holland. The year is 1908. The 10th of July, to be exact, a summer day outside, though inside this particular laboratory, the air around the apparatus is colder than anywhere else on Earth. The man at the heart of it is named Heike Kamerlingh-Onnes, and he has spent years, decades really, chasing this single moment. Because helium was the last holdout, the last of the gases. You see, by then scientists had learned how to take the air apart and turn each of its pieces into a liquid by chilling them far enough. They'd liquefied oxygen, nitrogen, hydrogen. One by one, the gases had surrendered to the cold and become liquids you could pour. Each one a little harder than the last, each one demanding a deeper cold. But helium had resisted them all. Helium clung to being a gas longer than anything else, refusing to condense, slipping away from every attempt, as if it didn't want to be caught. It was the very last permanent gas, the final stubborn one that no one had ever managed to turn into a liquid. And on that July day in 1908, Onnes caught it. After all the years, after all the careful, patient cooling, the helium gas in his apparatus finally gave way and gathered at the bottom of his glass into a small pool of clear liquid. Roughly 4.2 Kelvin, about 269 degrees below zero on the Celsius scale. A cold so deep it's hard to even hold in your mind. The coldest liquid anyone had ever made. The coldest place in that moment in the entire known universe, sitting in a glass in a quiet room in Leiden. It was an extraordinary thing to have done. So extraordinary that years later, in 1913, Ons would be given the Nobel Prize in Physics for it, for reaching down into a region of cold no one had ever touched and bringing something back. He had opened a door. He had made the doorway to the cold and walked through it and found a new liquid waiting on the other side. And here is what's so lovely, so quietly suspenseful about where he stood that day. He had reached 4.2 Kelvin. He had made the liquid. He was, in a sense, standing right at the edge of the most astonishing discovery in this whole story. And he didn't know it, because the wonders we've been circling, the climbing film, the silent stillness, the fountain that runs on light, none of those happen yet at 4.2 Kelvin. At 4.2, the helium is still, in most ways, a fairly ordinary liquid, a very, very cold one, but ordinary. It boils, it pours, it behaves itself mostly. The real strangeness is still hidden just a little further down. Ons was standing on the porch of the cold, holding the door open, with the strangest country in all of physics lying just beyond. And he couldn't see it yet. It was only 2 more degrees down, 2 more small degrees toward the silence. So we have our starting place, we have our restless little liquid that will not freeze, born in Leiden on a summer day, the coldest thing in the world, resting in its glass at 4.2 Kelvin, boiling gently, with no idea what it's about to become. And from here, the only way forward is down. We follow the temperature lower. We let the cold deepen, 1 careful fraction of a degree at a time, the way you might let yourself sink a little further into sleep. And as we go, something is going to begin to change in that quiet liquid. The boiling, that soft, busy bubbling, is going to grow uneasy. And then, at one particular temperature, a number we'll arrive at very soon, less than 2 full degrees below where Ons is standing right now, it's going to do something that the first time anyone saw it made them stop and stare and wonder if their eyes were lying to them. But I'm getting ahead of us, and there's no need to hurry. The cold is patient. The liquid isn't going anywhere, and neither for tonight are you. So let's just keep descending gently into the cold. Down past 4 Kelvin, down toward 3. The bubbling's still going, the liquid's still restless, the threshold still hidden somewhere below us in the dark and the quiet. And as we sink toward it, hold on to that one small, strange truth, the one that's going to explain everything that comes next, the soft, contrarian heart of this whole sleepy story. It isn't going to climb because something reaches up and pulls it. It's going to climb because down there in the deep cold, all the things that normally hold a liquid in its place are about to, one by one, quietly let go. 3 Kelvin, 2.8, 2.6. If you could stand at the edge of that flask and watch through the glass, through the cold, through all that carefully managed silence, the liquid would still look ordinary, pale, colorless, faintly restless. The surface dancing with fine, busy bubbles, the way water dances when a pot is just beginning to warm. Except here, of course, it's the opposite of warming. Here, the heat is being pulled away, slowly, methodically, the temperature falling through degrees and fractions of degrees, the way leaves fall in a still garden. One at a time, unhurried. The bubbles are still there, though. That's the important thing to notice. Even at 3 Kelvin, even at 2.8, the helium is still boiling, still active, still, in some ordinary physical sense, behaving itself, But something is coming. 2.5 Kelvin, 2.4, 2.2. You probably won't see it approaching. There's no visible tremor in the liquid, no shadow creeping across the surface, no gradual slowing of the bubbles. The change, when it comes, gives no warning. It doesn't taper, it doesn't fade, it just happens all at once, at one specific, precise, unrepeatable temperature, as though someone somewhere has thrown an invisible switch deep inside the physics of the thing. 2.17 Kelvin. The boiling stops. Not gradually, not the way a simmering pot settles when you turn the heat down a little, not with a few last bubbles rising and breaking at the surface before the liquid goes calm. It stops. All of it. Everywhere in the flask, simultaneously, in a single instant. And the liquid, which a fraction of a second before was active and restless and covered in that fine, living dance of bubbles, is suddenly and completely and utterly still. Glass flat at the surface, silent in a way that ordinary liquids simply are not. The scientists who first saw this in the 1930s in laboratories in Cambridge and Leiden and Moscow described it in different ways, but the word that kept returning was eerie. The stillness was eerie, because it wasn't the stillness of a liquid at rest, it was the stillness of something that had changed. The surface didn't just stop moving, it looked different, clearer, as though the liquid had become, in some way that had no precise name yet, more itself, or less ordinary, or simply other than what it had been a breath before. And then if you watched a little longer, you might notice something else. The level in the flask beginning very slowly, very quietly to drop. Not because the helium is evaporating faster, not because there's a crack in the glass, but because the liquid is climbing. Right now, at this moment, it's climbing the inner wall of the flask in a film so thin it's invisible to the naked eye, a film 30 nanometers thick, 30 billionths of a meter, a few hundred atoms piled on top of each other. And it's going up, over the rim, and down the outside, and dripping from the bottom onto the laboratory bench below, drop by patient drop. But we'll get to the climbing. We said we'd get to that, and we will. First, let's sit with this moment, this threshold, this temperature, 2.17 Kelvin. It has a name, they call it the lambda point, and the name is quietly beautiful because it comes from a curve. If you were to measure the amount of heat required to raise the temperature of liquid helium by a tiny increment, 1 degree, 1/10 of a degree, 1/100th, and you were to plot that measurement against temperature, drawing a graph of what physicists call specific heat, you would find, at the approach to 2.17 Kelvin, a curve that rises steeply from either side toward a sharp, dramatic spike, a peak so sudden and so tall it looks less like a graph of a physical quantity and more like a letter, the Greek letter lambda. L, that elegant upside-down V with its legs spreading slightly at the base. The physics wrote its own symbol on the graph, so they named the temperature after it, 2.17 Kelvin. Or, if you want the full precision, and there is something lovely about how precise it is, how exact and uncompromising the universe is about this particular number, 2.1768 Kelvin, that's it. That's the line. That's where one thing ends and another begins. And to put it in terms your body might feel, 2.17 Kelvin is approximately minus 271 degrees Celsius, less than 2 full degrees above absolute zero. Absolute zero is the coldest temperature that the laws of physics permit to exist, the point at which all thermal motion, all heat-driven vibration, has been drained from a substance completely. 2.17 Kelvin is so close to that limit that the gap between them is smaller than the gap between a warm bath and a cool room. It's the very bottom of what's possible, and right there, at the edge of existence, the helium changes. Above the lambda point, liquid helium-4 is called helium I. It's an ordinary, if extraordinarily cold, liquid. It obeys the same rules as any other fluid. It has viscosity, the internal stickiness that makes fluids resist flowing, makes them cling to walls, makes them respond to gravity and friction the way all sensible liquids do. Helium boils, helium behaves. Below the lambda point it's called helium-2. And helium-2 is something else entirely. It belongs to a different category, though for many years nobody had a category adequate to put it in. It looks like a liquid. It fills its container like a liquid. If you had no instruments and only your eyes, you might not immediately know that anything had changed except for that sudden, disturbing stillness where the bubbling used to be. But helium-2 is not, in any physically meaningful sense, a colder version of helium-Y. It's a new phase of matter, a thing with properties that have no precedent in ordinary experience, properties that seem, at first encounter, like conjuring tricks or mistakes or both. The most immediate of those properties is this: helium-2 has no measurable viscosity. None. Not very little. Not negligibly small. The viscosity, when measured by the most sensitive methods available, falls to a value consistent with exactly 0. It flows through channels and pores and cracks that are so fine, so narrow, that no ordinary liquid, not water, not oil, not liquid nitrogen, not even helium could pass through them. It doesn't just flow easily, it flows as though the concept of resistance has been quietly removed from its physics. The internal friction that makes other liquids slow down, that makes them cling to surfaces, that makes them expensive to push, that friction is simply, precisely, completely absent. This is not a poetic exaggeration. This is what the measurements show. A flow set in motion in a closed loop of superfluid helium-4 will continue flowing without slowing for as long as the helium remains cold. Not for hours, not for days, for as long as you keep it below the lambda point, which in a properly maintained cryostat could, in principle, be indefinitely. There is no friction to drain the motion away. The flow has nothing to push against. The experimenters in the 1930s did not accept this easily. It was too strange. Viscosity is one of the most basic properties of a liquid, the thing that makes fluids feel like fluids, the thing that gives them resistance and body and substance. A liquid without viscosity is, in the language of ordinary intuition, barely a liquid at all. It's more like a dream of a liquid. But the measurements were clear, and they were being made independently in different countries by different people with different equipment, and they were all arriving at the same impossible answer. It's worth pausing here to tell you how this discovery happened, because it didn't happen in a single quiet moment of revelation in a single laboratory. It happened in two places at once, in 1938 in what is one of the stranger coincidences in the history of physics. Though perhaps coincidence isn't quite right, because both groups of scientists were following the same thread, the same anomalies, the same strange behaviors that liquid helium had been displaying since ONS first made it in 1908. The question had been sitting in the physics community for 30 years. Two groups simply answered it at the same moment. The first paper came from Moscow. It was written by Pyotr Kapitsa, a physicist whose story we should spend a moment with, because it is as remarkable in its own way as the discovery itself. Kapitsa had spent the 1920s and much of the 1930s working at the Cavendish Laboratory in Cambridge, which was at that time the most celebrated physics laboratory in the world, led by Ernest Rutherford, the man who had split the atom. Kapitsa had become one of Rutherford's most valued researchers, inventive, bold, a brilliant experimentalist with a gift for building instruments that could push physical conditions to their very limits. He was, by any measure, at home in Cambridge. He had a laboratory there, a flat there, friends there, a life there. And then in the summer of 1934, he went home to the Soviet Union to visit his family. He did not come back. The Soviet government, without warning, without stated justification, revoked his exit visa. He was not arrested, he was not imprisoned. He was simply held, not allowed to return to England, not told when or whether that might change. A scientist at the peak of his powers, suddenly cut off from his laboratory, his equipment, his colleagues, his work. Rutherford protested on his behalf. Other scientists wrote letters. None of it made any difference. What happened next says something generous about science and something complicated about governments. Rather than simply lose Kapitsa's abilities to enforced idleness, the Soviet Academy of Sciences built him a new laboratory in Moscow, the Institute for Physical Problems, founded in 1935. And Rutherford, in an act that combined pragmatism with a kind of grief, agreed to sell Kapitsa's Cambridge equipment to the Soviet government so that it could be shipped to Moscow and reassembled there. The instruments that Kapitsa had spent years designing and refining, the very tools of his craft, traveled east to meet him. In his new Moscow laboratory, with his own equipment around him again, Kapitsa returned to the problem of liquid helium. And in 1937 and early 1938, he conducted the experiments that settled the question. He measured the flow of helium-2 through fine channels. He measured the viscosity. And the viscosity was zero, or as close to zero as his instruments could detect, which was extraordinarily close. He wrote up his results and submitted them to Nature, the British scientific journal. And the paper appeared in January 1938. In the same issue of Nature, the same journal, the same month, a second paper appeared. This one came from Cambridge. John F. Allen and Don Missener, working at the Cavendish laboratory that Kapitsa had left only a few years before, had independently arrived at the same conclusion. Helium-2 had no viscosity. It flowed without friction. 2 experiments, 2 countries, 1 answer. Kapitsa's paper went further in one way. It gave the phenomenon its name. Drawing on the recently discovered phenomenon of superconductivity, the ability of certain metals at very low temperatures to carry electrical current without any resistance at all, Kapitsa coined the word superfluidity. A superfluid, by analogy, is a fluid that flows without friction, without resistance, without any of the ordinary drag that fluids accumulate as they move. The word was precise and evocative in equal measure, and it has been the word ever since, superfluidity. The name sounds almost like something out of a dream, doesn't it? Something with the prefix super attached to an ordinary noun, the way we do when we can't quite believe that the real version of a thing is actually possible. Superman, superconductor, superfluid, as though the universe occasionally outdoes itself. Kapitsa received the Nobel Prize in Physics for this discovery, not in 1938 when the discovery was made, not in the 1940s when the theoretical explanation was developed, in 1978, 40 years later. He was 83 years old. He had been nominated many times over those decades and had not received it, for reasons that almost certainly had something to do with the political complexities of the Cold War and the particular awkwardness of honoring a prominent Soviet scientist at the height of Soviet Western tensions. In 1978, the committee finally gave it to him. He accepted it with characteristic directness and a dry wit that had never, apparently, deserted him. There's something in that delay that seems quietly appropriate for a story about liquid helium. The patience of it, the long wait, the eventual arrival of recognition, just as the thing itself waited 30 years after Ons first made the liquid before anyone figured out what it truly was. But we should go back to the flask, back to the laboratory, back to the liquid. Because here is what no one in 1938 could yet explain. Why? Why does the viscosity vanish? Why does this specific element, at this specific temperature, do something that no other substance had ever been observed to do? Kapitsa and Allen and Missener could describe the phenomenon with beautiful precision. They could not explain it, and the description alone, this liquid with no friction, this fluid that slips through the smallest imaginable gaps, was already straining at the edges of the available physical vocabulary. The experimenters in Cambridge in the 1930s found themselves facing a more immediate puzzle alongside the theoretical one. Their carefully designed and supposedly sealed glass containers were mysteriously emptying. The level of helium-2 would drop when it shouldn't. The liquid was escaping. Not violently, not explosively, but quietly, steadily, in ways that no ordinary fluid could manage. It was seeping through places that by any reasonable standard should have been impermeable. Checking the seals, checking the glass, checking the fittings, and everything appeared intact, and yet the level kept falling. For a while this was maddening. The assumption was that something in the apparatus was leaking. That's the sensible assumption. If a liquid is escaping, there must be a gap. Find the gap, seal it. But the gaps, when they existed at all, were so small, so unimaginably fine, that no ordinary liquid could possibly have passed through them. And that, of course, was the clue that nobody quite recognized immediately as a clue. Because in ordinary experience, if the gap is too small for the liquid stays where it is. That is what liquids do. Helium-2, it turned out, does not do that, because it has no viscosity to resist the flow, because there is no internal friction to make the journey through a tiny pore energetically costly. It flows through openings that ordinary physics would call effectively sealed. It doesn't force its way through. It doesn't need to. It simply goes the way a thought slips through a moment of drowsiness, without effort, without resistance, as though the barrier were not quite entirely there.
And the film on the walls. That was the other piece of the puzzle, and it took a little longer to understand. The liquid wasn't only escaping through invisible cracks, it was climbing, spontaneously, continuously, silently, up the inner walls of any container it was placed in a film so thin, roughly 30 nanometers, remember? A few hundred atoms standing shoulder to shoulder, that it was essentially transparent, essentially weightless, essentially invisible against the glass.
Bernard Rollin had been studying this film in the late 1930s, and his work gave it a name it carries to this day, the Rollin film. And the Rollin film has a quality that is, once you hear it, even harder to dismiss than the zero viscosity. The film doesn't just climb, it climbs at a specific speed, roughly 20 to 30 centimeters per second, and that speed is constant. It doesn't slow down for a higher wall, it doesn't speed up on a shorter one, it creeps at its characteristic pace regardless of the geometry, regardless of the height it has to cover, because the thing that would normally slow a climbing film, the thing that would drain energy from the motion, that would make the climb harder the higher you went, is gone. The viscosity is gone, the friction is gone, and in the absence of those things, height means almost nothing. Think about that for a moment. If you're still with me, if you haven't already begun to drift, every other liquid that has ever crept up any surface in the history of the universe has had to pay a price for each centimeter of height. Gravity costs something, overcoming friction costs something. The higher you climb, the more you spend. This is why water doesn't climb out of glasses. This is why no liquid, in ordinary experience, can raise itself above its own surface level in an open container, beyond the tiny surface tension-driven capillary effects you might see in a narrow tube. Liquids stay where they are because the physics keeps them there. The Rollin film does not stay where it is. It pays no price for height. The film keeps climbing because there is nothing to stop it, and it drains itself over the rim and down the outside of the container, drop by patient drop, until the container is empty. And the really extraordinary thing, the thing that completes the picture, is that the flow isn't going up because something is pulling it. There's no mysterious attractive force acting on the walls of the flask, summoning the helium upward against gravity. Gravity is still there. Gravity is still doing exactly what it always does. The helium still falls when it gets over the rim and down the outside. You can see it dripping from the bottom, falling under gravity just as it should. What's different is not the presence of some new upward force. What's different is the absence of resistance. The film climbs the wall because the film can climb the wall, because there is no viscous drag, no internal friction, no energy cost to the motion that would normally make climbing expensive enough that the liquid gives up and stays put. Remove the friction, and the helium does what any liquid would do if it could. It follows the slight surface attractions, the tiny van der Waals forces between the helium atoms and the glass, which are always present in any liquid against any surface, but which are normally far too feeble to pull a viscous liquid upward against gravity. In helium-2, those feeble forces are enough because there's nothing fighting them. It climbs not because it is pulled, it climbs because nothing stops it. That's the thought I want you to carry with you as you settle a little deeper into wherever you are tonight. That's the quiet, precise inversion at the heart of this whole story. The mystery of the self-emptying cup is not the mystery of a new force. It's the mystery of an absent resistance. Something is missing from the physics below 2.17 Kelvin, and that missing thing is what we ordinarily call normal. The ordinary drag, the ordinary friction, the ordinary cost of motion. And so the liquid does what all liquids would do, have always wanted to do if only the physics would let them. It goes everywhere it can. The question of why, the deep, satisfying answer to why this happens below and only below that precise temperature, would have to wait. In 1938, the phenomenon had been described with exquisite accuracy. It had been named, but the machinery underneath it, the reason that this element at this temperature should shed its viscosity like a coat it no longer needed, that was still dark. It wouldn't stay dark for long, but that part of the story belongs to the next part of our descent. For now, let's just remain here at the threshold. 2.17 Kelvin, the liquid going still, the bubbles stopping, the film beginning, invisibly, to climb. Imagine the laboratory as it might have been in Cambridge in 1937 or 1938. Cold in the ordinary English sense of the word, a drafty room, stone floors, the smell of chalk and metal and something chemical underneath everything. And in the middle of it, inside insulation carefully layered against the intrusion of warmth, a flask of liquid helium smaller than a coffee cup. The temperature falling, the equipment watching, and then at that one precise number, either 2.17, the change. The scientists who saw it for the first time knew they were seeing something real. They also knew they didn't fully understand it. Both those things were true simultaneously, and in the history of physics, that particular combination, something unmistakably real, something not yet understood, is among the most productive states a scientist can be in. It means there is work to do. It means the physics is showing you something new. What they had by the end of 1938 was this: a confirmed observation, a name, and a set of measurements precise enough to rule out the ordinary explanations. Helium-2 was not just cold helium with low viscosity, it was something categorically different. The viscosity wasn't reduced, it was gone. And the transition between helium-Y and helium-2 wasn't gradual. It happened at an exact point, as sharp as a knife's edge, as sudden as a switch. That sharpness matters. It tells you that the change isn't a matter of degree, but a matter of kind. Helium-I and helium-2 are not points on a continuum like ice and cold water and warm water and steam, all made of the same molecular water at different temperatures. Helium-I and helium-2 are distinct phases, the way solid and liquid are distinct phases, the way a thing can be one thing and then be something genuinely other. The lambda point is a phase boundary, a line the universe draws in the temperature axis, a line that says, here and only here, something qualitatively changes. And when you think about it that way, when you think about phase boundaries, about the way matter can reorganize itself at a threshold into something with wholly different properties. The strangeness of helium-2 starts to feel less like magic and more like physics at its most decisive. Physics, when it changes phase, is thorough about it. The boiling stops because of something we'll come to soon, a property of helium-2 as a heat conductor that is, in its own way, as astonishing as the zero viscosity. The reason the surface goes suddenly glassy and still has to do with how heat moves through the liquid, or rather how implausibly fast it moves. But let's not arrive there quite yet. Let's hold that loop open a little longer, carry it with us further into the cold, let it wait for us the way the answer to a riddle waits. Patient, present, not yet spoken. Kapitsa in Moscow had the answer to what the liquid did. He did not have the answer to what the liquid was. He had named it superfluidity and measured its most dramatic property. But the theoretical framework that would explain why the viscosity vanished, why the lambda point was exactly where it was, why helium specifically and no other common substance at any other temperature, that framework had not yet been built. And in a broader sense, the physics community in 1938 was only just beginning to have the tools that such a framework would require. Quantum mechanics, the strange, probabilistic, wave-based description of matter at the smallest scales, had been developed over the previous 15 years, and it had been spectacularly successful at explaining the behavior of electrons, atoms, and light. But applying quantum mechanics to a liquid, to a macroscopic collection of billions upon billions of atoms, all interacting with each other, was a different and much harder problem. Quantum effects in most substances are confined to the microscopic world. They average out, they cancel, they get washed away by the thermal chaos of ordinary temperatures, and the macroscopic world behaves classically as a result. Except, apparently, when it doesn't. Except at 2.17 Kelvin in a flask of liquid helium-4, where the quantum effects don't wash out, where they scale up, where they manifest at the size of a teacup, visible to the eye, measurable with ordinary instruments, undeniable. That is what makes helium-2 so philosophically strange and so beautiful. It is not merely a curiosity of low-temperature physics. It is a demonstration, the clearest demonstration that nature provides at any temperature a laboratory can achieve, that quantum mechanics is not only the physics of the very small. Under the right conditions, quantum mechanics is the physics of the very cold. And the very cold, it turns out, can be as large as you like. But the explanation, or the theoretical machinery, the model that would finally make sense of all of it, belongs to a man named Lev Landau, and to the year 1941, and to a chapter of this story that will open shortly. Let Landau wait for a moment, the way the best explanations always make you wait a little, so that when they arrive, they feel earned. For now, just this. In January 1938, 2 papers in one journal changed what physicists thought was possible. In Moscow, Pyotr Kapitsa, detained, separated from his Cambridge life, rebuilding his work in a new country, a man who had good reason to be bitter, and who seems, by the accounts of those who knew him, to have channeled all of it into ferocious, precise, elegant experiment, published his measurements of something he called superfluidity. In Cambridge, John Allen and Don Misener published theirs. 2 sets of hands, 2 sets of instruments, 1 answer. The liquid could not be held. It flowed through anything. It climbed its own walls. It emptied its own containers. And it had a name. And somewhere in Cambridge and Moscow and every other cryogenics laboratory that received that issue of nature in the first weeks of 1938, physicists set down the journal and looked at their own equipment and began to ask a question that would take years and a great deal of cold to properly answer. Why? There is something almost restful about that moment of naming, isn't there? Before the why is settled, before the full explanation has been worked out and tested and confirmed. There is this brief, suspended time when the phenomenon exists as pure observation, when you know that something extraordinary is happening and you can say its name and measure its properties and wonder at them without yet having to explain them away. Superfluidity. It's a good word to fall asleep to. You could say it softly to yourself, there in the dark, wherever you are tonight, in your corner of the world with whatever the hour is bringing you, whether it's a late city or a quiet countryside or the particular stillness of very early morning. Superfluidity. Something without friction. Something that goes and keeps going because nothing is there to stop it. Below 2.17 Kelvin, where the boiling stops and the liquid falls silent, where the ordinary rules have, one by one, quietly stepped aside. We're still descending, there's still further to go. The full picture, the two-fluid model, the thermal mystery, the light-powered fountain, the quantum wave function that stretches the size of a cup, all of that is waiting for us, just a little deeper into the cold. But for this part of our journey, let's rest here for a moment, at the lambda point, at the threshold, at the eerie, glass-smooth surface of helium-2, sitting perfectly still in its flask, its invisible film already beginning its quiet, tireless, unstoppable climb. The name is on the page, the phenomenon is real, and the reason, when the deep, strange, beautiful reason, is coming. And the reason, when it comes, arrives the way the best explanations always do. Not as a sudden jolt, but as a slow clearing, like a fog lifting from a familiar landscape until you see the shape of something that was always there. It arrives in the form of a man sitting in Moscow in 1941, during one of the strangest and most terrible years of the 20th century, doing what he could only have done in the quiet hours between catastrophes. His name was Lev Landau, and what he gave the world was not just an explanation of superfluid helium, it was a new way of thinking about matter itself. Landau was already by 1941 one of the most formidable theoretical physicists in the Soviet Union. He was 33 years old. He had been through things that would have broken most people, including a year in one of Stalin's prisons just 3 years earlier, on charges that were as meaningless as most such charges were in that era. He had been released in 1939, partly through the personal intervention of Kapitsa, who had vouched for him to the authorities. And now here he was, back at work, carrying in his head the experimental results that Kapitsa had been sending him, and trying to find the mathematical skeleton underneath the extraordinary behavior of helium-2. What Landau built over the course of 1941 became known as the two-fluid model, and it is one of those theoretical achievements that you can explain to someone in a few minutes, and they will understand it, and then they will sit quietly for a moment, because they will realize they have just understood something genuinely strange. Here is the picture. Imagine your cup of helium-2 sitting perfectly still below 217 Kelvin. The liquid looks like one thing. It takes up space, it has weight, it reflects light, it behaves in most ordinary ways like a single fluid in a single cup. But Landau's insight, the thing that made the mathematics work, the thing that accounted for every odd measurement the experimenters were sending him, was this. Inside that cup, there are not one, but two fluids. They occupy the same space, they pass through each other without interaction, they can flow in opposite directions simultaneously through the very same channel without interfering with one another in any way that creates friction. And they are not separate chemical substances, but they are both just helium-4 atoms, the same atoms, but they are behaving according to two completely different sets of rules. The first is what Landau called the normal component. It behaves exactly the way you'd expect a cold liquid to behave. It has ordinary viscosity, it carries heat, it sloshes around, drags on surfaces, and does all the things that fluids do when they have internal friction to govern them. Nothing mysterious about the normal component at all. The second is the superfluid component, and this one has zero viscosity. Not very low viscosity, not the viscosity of a gas, or of a very smooth oil, or of anything you have encountered before in ordinary life. Zero. It also carries zero entropy, which means it carries zero heat. It flows without any internal resistance through any channel past any surface without losing a single fraction of its momentum to anything. And the ratio of these two components, how much of the cup is normal fluid and how much is superfluid, depends entirely on temperature. Right at the lambda point, at 2.17 Kelvin, the superfluid component is essentially absent. All of the liquid is behaving normally as helium I does. Then, as the temperature drops, the superfluid fraction begins to grow, slowly at first, and then more steadily. The normal fraction shrinks as the superfluid fraction expands, like two dancers trading places in an infinitely slow exchange. By the time you approach absolute zero, as close as you can get to it, the normal fraction has nearly vanished. The liquid is nearly 100% superfluid, nearly completely without viscosity, nearly completely without friction. This is why helium-2's behavior changes so dramatically with temperature. It's not one thing changing, it's the proportions of two things changing, and you are seeing the superfluid fraction's properties become more and more dominant as it claims more and more of the liquid. Landau received the 1962 Nobel Prize in Physics for this work, for his theories of condensed matter, and especially for this picture of liquid helium. The Nobel Committee waited 21 years. In that time, the model had been confirmed and tested and built upon so many times that it had become the foundation of an entire field. Landau himself had survived the war, survived Stalin's USSR, survived a terrible car crash in 1962 that left him in a coma for weeks and from which he never fully recovered. He was unable to travel to Stockholm to receive his prize. The diploma and the medal were brought to him in his hospital room in Moscow. He died in 1968, but the two-fluid model survives as clean and vivid as the day he wrote it down. Now, you have been sitting here with this picture. Two fluids, one normal, one without friction, trading places as the temperature falls. And perhaps a question has been forming slowly in the back of your mind. Because this model describes the behavior beautifully, and it gives you a framework for thinking about the measurements, but it doesn't quite tell you why. Why should there be two components? Why does this superfluid fraction grow as the temperature falls? Why zero viscosity and not just very low viscosity? Those questions are waiting for us and we will reach them. But first, let's use the model to understand the thing you have been watching since the very beginning of our journey tonight. Let's use it to understand the film. The Rollin film, you'll remember, is the creeping skin of helium that climbs the walls of any container in which helium-2 sits. It's about 30 nanometers thick, a few hundred atoms, and utterly invisible to the naked eye. But it is there. It is always there. And it is moving. And now we can say why. The film is superfluid component. Only the superfluid component creeps in this way because only the superfluid component has zero viscosity. The normal component sits in the bulk of the liquid, sluggish and ordinary, doing nothing particularly dramatic. But the superfluid component spreads and wets every surface it touches, driven by ordinary atomic attractions. The same van der Waals forces that make liquids cling to surfaces in general. And because it has no viscosity, nothing slows its spread. There is no internal resistance. There is no friction with the glass to slow it down. There is nothing to stop the film from climbing as long as a surface exists to climb. Think about what viscosity normally does for a liquid climbing a surface. Honey climbing a wall. You can picture how slowly that would go. Water climbing a wall. Better. but still the friction between water molecules and glass, the internal friction between water molecules and each other, all of that creates a resistance that limits how far and how fast the water can climb. Even very runny liquids are limited by their own viscosity and how far they'll go before the gravitational pull downward, and the internal drag balance the surface forces pulling upward. Now remove viscosity entirely, not reduce it, remove it. The surface forces, or the atomic attractions between the helium and the glass, are enough to pull the film upward, and there is nothing to resist that pull, nothing to slow the film's climb, nothing to say at any point along the way, "This is far enough." Friction claims the rest. So the film climbs all the way. It climbs over the rim of the container, and when it spills over the rim, gravity pulls it down the outside of the wall. And again, there is no friction to slow the descent. The film flows down the outside of the cup, gathers at the lowest point, and drips. Drop after drop, slowly, silently, the helium empties itself out of its own container and onto whatever is below. And if there is a warmer surface below, than almost anything, even the floor of the lab is warmer than helium-2, the droplets evaporate on contact. The speed at which the film creeps is remarkably consistent, around 20 to 30 centimeters per second. And here is something worth pausing on, because it's the kind of detail that sounds impossible until you think about what zero viscosity means. The film moves at roughly the same speed regardless of the height it has to climb. For an ordinary liquid, this makes no sense. For ordinary fluids, a greater height means a greater resistance. You'd need more force to push the liquid higher, and the flow rate would change accordingly. But the Rollin film doesn't care about height. It moves at its characteristic speed, whether the cup is 2 centimeters tall or 20. Because what determines its flow rate is not the gravitational challenge that exists for all liquids, but the film's own cross-section and the absence of anything to oppose its motion. The flow rate is set by how much superfluid film is there to flow, not by how far it has to go. It climbs because nothing stops it. That's it. That's the whole reason. Not a special upward force, not anything that has overcome gravity. Gravity is still there, pulling in exactly the direction gravity always pulls. But the usual balance, gravity on one side, friction and viscosity and internal drag on the other, that balance has been broken. Not because gravity weakened, because friction vanished. And so the film climbs. Bernard Rollin, who studied this phenomenon in the late 1930s, put his name to it. He worked carefully through the properties of this creeping skin, its thickness, its speed, the way it behaves, and gave future physicists a framework for thinking about it. He deserves his place in the story. The experimenters of that era, puzzling over flasks that kept mysteriously emptying, slowly worked out that the culprit was not some leak in their apparatus, but the liquid itself, creeping out through routes no ordinary liquid could take. It's a gentle correction to something the physics doesn't need to embellish. The actual facts are remarkable enough. A liquid that climbs its own walls in a film a few hundred atoms thick at a steady 20 to 30 centimeters per second, indifferent to height, until the container is empty. That is real, and it happens in any properly cooled lab, reliably, every time. No embellishment needed. Now, let's stay inside the cup for a moment longer, because there is something else the two-fluid model reveals that is almost as strange as the climbing film, and it has to do with heat. You have probably noticed by now, if you've been following our journey tonight, that helium-2 has a peculiar relationship with heat. We've mentioned in passing that the boiling stops at 2.17 Kelvin, that the vigorous, roiling surface of the liquid suddenly goes still the moment the temperature crosses the lambda point. And we said this would need an explanation. Here it is. Helium-2 is the best thermal conductor known to physics. Not simply a good conductor, not the best liquid conductor or the best conductor. in its temperature range, but the best thermal conductor known, several hundred times better than copper at room temperature. And copper is already one of the best thermal conductors in ordinary engineering. We use copper to carry heat away from electronics, to make radiators, to build heat exchangers. Copper, at room temperature, conducts heat far better than wood, or glass, or water. And helium-2, at its cryogenic temperatures, conducts heat hundreds of times better than that. Heat does not diffuse slowly through helium-2 the way it diffuses through water, or through copper, or through almost any other material. When a source of heat touches helium-2, the heat is carried to the surface and dispersed almost instantaneously. The response time is so fast and the conduction so perfect that it is physically impossible for a temperature difference large enough to nucleate a bubble to exist anywhere inside the bulk of the liquid. And bubbles require exactly that, a local hotspot, a pocket of liquid where the temperature is high enough for the liquid to vaporize before the surrounding cooler liquid can absorb the excess energy. In helium-2, no such hotspot can persist. Heat is gone before the bubble forms. This is why helium-2 cannot boil in the conventional sense, not because it lacks the energy where you can add heat to it, but because the liquid's own extraordinary thermal conductivity carries that heat to the surface and turns it into evaporation before it can turn it into bubbles. The boiling happens, in effect, at the surface only, not throughout the bulk. And so the surface is still and the bulk is still and the liquid looks, to a newcomer, to a physicist seeing it for the first time, as though the heat has somehow stopped working. It hasn't. It's working faster than you've ever seen heat work. And now Landau's two-fluid model helps here too, in a way that feels almost like magic until you see the logic. When heat enters helium-2, it does something specific. The heat disturbs the superfluid component, not by creating a hotspot, but by temporarily converting superfluid fraction into normal fraction. A bit of locally heated helium becomes more normal component and less superfluid component, because the normal component carries entropy and heat, and the superfluid component does not. So the heat, in a sense, is temporarily stored in the normal component. And then something happens that does not happen in any other liquid. The normal component, being warm, flows toward the colder regions. The superfluid component, being cold, flows toward the warmer regions to replace what was converted. They flow in opposite directions through the same channel simultaneously, as only two interpenetrating frictionless and friction fluids can. The heat is carried outward, the cold is carried inward, the balance is maintained. And this happens so quickly over such short distances that the temperature inside the bulk of the liquid stays very nearly uniform throughout. It is as though the liquid has an internal circulation system designed specifically to carry heat away before it can do any damage, which in a sense, it does. The two-fluid nature of helium-2 is exactly that system, but the most remarkable consequence of all this, and the one that Landau predicted theoretically, and that a physicist named Vasilii Peshkov confirmed experimentally in 1944, is what the model implies about how heat propagates through helium-2. In ordinary matter, heat propagates by diffusion. Molecules bump into each other, sharing energy, and the warmth spreads outward the way ink diffuses in water, gradually, in all directions, fading as it goes. There is no wave of heat in ordinary materials, there is only a spreading, blurring distribution. But in helium-2, the two-fluid exchange to the superfluid flowing toward heat, the normal component flowing away from it in perfect synchrony, creates something fundamentally different. It creates a wave, not a pressure wave like sound, a temperature wave, a wave in which alternating regions of slightly warmer and slightly cooler helium propagate through the liquid the way an ordinary sound wave propagates through air, as a genuine oscillation back and forth with a measurable frequency and a measurable speed. The regions of warmth and coldness are not spreading and diffusing. They are oscillating. They are genuinely, thermodynamically, wave-like. Landau called this second sound by analogy with ordinary sound, which he called first sound. First sound is a pressure wave. Second sound is a temperature wave. They are both real propagating waves in helium-2. They exist in the same liquid at the same time, traveling at different speeds, carrying different physical quantities, one carrying pressure, one carrying temperature, and both as real and measurable as the acoustic vibrations of the air around you. Second sound, what a name! It sounds like something from a poem about the end of the world or from a story about physics that is being invented as you dream. But it's real, it was predicted, it was measured. Vasilii Peshkov detected it experimentally, confirmed its properties, measured its speed, and showed that Landau's prediction was correct in every testable detail. And what Peshkov found was that second sound in helium-2 travels at roughly 20 meters per second near absolute zero, a speed comparable to ordinary sound in some materials, but carrying nothing but temperature.
Imagine it. A wave of warmth traveling through a liquid, not spreading, not diffusing, but propagating. Hot, cold, a genuine oscillation of temperature moving through the cup like a ripple. If you could see it, if your eyes were sensitive to temperature the way they're sensitive to light, you would see what looked for all the world like a sound wave, but made of heat instead of pressure.
This is what helium-2 does with the heat you give it. This is why it can't boil. This is why it conducts heat so extraordinarily well. And this is one of the phenomena, like the climbing film, like the fountain, like the persistent flow, that the two-fluid model predicted and that experiments confirmed, and that sits at the edge of what ordinary intuition can accommodate. We should rest here for just a moment. You are, if our journey has gone well, somewhere comfortable tonight, wherever you are, whatever the hour, with the lamp perhaps dimming a little in your corner of the world. And it's worth noting, not as a lecture, but as something to carry into sleep, that what we have covered so far, all of it, is derivable from Landau's picture. From two fluids, one normal and one superfluid, sharing the same space. That simple, strange, mathematically elegant picture contains within it the climbing film, the perfect heat conduction, the second sound, and more that we haven't reached yet. A model that predicts this many things correctly in this much quantitative detail is not a guess. It is not hand-waving. It is a piece of deep insight about the structure of matter confirmed over and over in experiments conducted across decades and continents. But Landau's model is still not the whole story. It is a correct description of how helium-2 behaves. What it doesn't yet fully reveal is why helium-4 atoms, of all things, should spontaneously organize themselves into a superfluid component with zero viscosity. The model says that this component exists and describes its properties with precision. But the deeper question, well, what is it at the level of the atoms themselves that makes the superfluid component possible, requires one more idea. And that idea is perhaps the most quietly astonishing one in this entire story. To understand it, you need to know one fact about helium-4 atoms. Just one. It will seem dry when I first say it, but stay with it, because the consequences are enormous. Helium-4 atoms are bosons. The word comes from Satyendra Nath Bose, whose work in the 1920s, developed together with Albert Einstein, led to the theoretical prediction of a new state of matter. To be a boson means to have an integer total quantum spin, 0 or 1 or 2, as opposed to a half-integer spin, which makes you a fermion. Electrons are fermions, protons are fermions, neutrons are fermions, but helium-4 atoms, because of the way their constituent parts add up, end up with an integer spin. This matters because of a deep rule in quantum mechanics about how identical particles can behave. Fermions, particles with half-integer spin, obey a rule called the Pauli exclusion principle. No two fermions can occupy the same quantum state simultaneously. This is why atoms have the structure they do. Electrons fill shells, pushing each other into higher and higher energy levels because no two electrons can share the same state. It's also why matter is solid. It's why you can sit on a chair. Without the exclusion principle, electrons would all pile into the lowest energy state and matter would collapse. Bosons have no such restriction. In fact, bosons have exactly the opposite tendency. They prefer, in a precisely quantifiable mathematical sense, to be in the same state as other bosons. The more bosons that are in a particular quantum state, the more strongly each additional boson is attracted to join them there. It is as though bosons are social in a way that fermions are not. Fermions spread out by rule, bosons crowd together by preference. Einstein took Bose's statistics and worked out what they implied for a gas of bosonic atoms, cooling toward absolute zero. What he found in 1924 and 1925 was a theoretical prediction that below a certain temperature, a macroscopic fraction of the bosons would all fall into exactly the same quantum ground state, the lowest possible energy state, simultaneously. Not a few atoms, not a percent or two. A genuine, large, macroscopic fraction, potentially all of them. All falling into one state, becoming, in a quantum mechanical sense, indistinguishable, identical, a single collective entity rather than a collection of separate particles. This was called Bose-Einstein condensation. It was predicted in 1924 and 1925. It took decades to confirm experimentally in dilute atomic gases. The confirmation came in 1995 in a beautiful series of experiments for which Eric Cornell, Carl Wieman, and Wolfgang Ketteler received the Nobel Prize in 2001. But in helium-4, the signal of something like Bose-Einstein condensation was already visible in a different and more complex form in the behavior of helium-2 that Kapitsa and Allen and Meissner were measuring in 1938. Here is what Bose-Einstein condensation means for liquid helium-4 below the lambda point. A fraction of the helium-4 atoms, not all of them, because in a liquid, the interactions between atoms complicate matters considerably compared to a dilute gas, but a meaningful fraction with ton falls into the same quantum ground state. And when they do this, they share something extraordinary. They share a wave function. In quantum mechanics, everything that exists has a wave function, a mathematical description of its quantum state, which encodes information about its position, momentum, and other properties in the form of a spread-out, wave-like distribution. An individual atom has its own wave function describing where it is likely to be and how fast it is likely to be moving. These individual wave functions are normally independent of each other. One atom's wave function does not know about another atom's wave function. They are separate entities, going their separate ways. But when many atoms condense into the same quantum ground state, when they all share the same quantum state, their individual wave functions merge into a single collective wave function, a shared wave function, a single mathematical description that describes all of the condensed atoms at once, as if they were one thing. And this shared wave function is not the size of an atom. It is not the size of a handful of atoms. It is the size of the container. It stretches across the entire sample of superfluid helium from wall to wall, touching every boundary, coherent throughout. A quantum object the size of a teacup. This is the deep truth beneath the two-fluid model. This is what the superfluid component actually is. It is the fraction of helium-4 atoms that have condensed into a single shared quantum state and are described by a single wave function stretching across the whole liquid. And now everything else follows. A single quantum object, described by a single coherent wave function, cannot be stopped by friction in the way that ordinary matter can. Ordinary friction is a process of energy transfer. A moving molecule hits a wall, loses some of its energy to the vibrations of the wall's atoms, slows down a little. Another molecule hits the wall. Another. Slowly, the energy of motion drains away into heat. This is viscosity at the molecular level. This is why things stop. But a coherent quantum state cannot lose its motion this way. The whole condensed fraction would have to scatter simultaneously, all of them, the entire collective object, in order for any energy to be lost. The mathematics of quantum mechanics makes this essentially impossible. At low energies, the condensate flows and flows and flows, because nothing can take its energy away in the small, gradual, piecemeal way that friction works. Zero viscosity, not approximately, 0, 0. And now the Rollin film makes even deeper sense. The superfluid fraction will use the condensate, wets the walls, spreads, climbs. And because it is a coherent quantum state, it cannot be slowed by the interaction with the glass. The van der Waals forces pull it up. There is no friction to stop it. The quantum coherence of the condensate protects its flow, and so it goes, up the wall, over the rim, down the outside, and off into the air. The film is not defying physics, it is obeying quantum mechanics so completely, so without exception, that everything we ordinarily think of as resistance, as the ordinary price a fluid pays for moving through the world, simply doesn't apply. Lev Landau's two-fluid model gave us the vocabulary and the quantitative framework. Bose-Einstein condensation gives us the reason. Together they tell us what is actually happening inside that quiet, glass, smooth cup of helium-2 below 217 Kelvin. A fraction of the liquid has condensed into a single shared quantum state, a coherent wave function the size of the container. That fraction has no viscosity and no entropy. It creeps up walls and flows through cracks and carries no heat and stops for nothing. And as the temperature falls further and further below the lambda point, that fraction grows, claiming more and more of the liquid until near absolute zero the cup is nearly entirely quantum. The other fraction, the normal component, is the rest. The atoms that haven't condensed yet, that are still behaving thermally, still carrying entropy and viscosity and all the ordinary properties of matter. They sit in the same cup, flowing through the same space, interpenetrating the condensate without interfering with it, because the condensate's quantum coherence keeps it separate in the way that matters. There is something almost peaceful about this picture, if you let yourself sit with it. Below 217 Kelvin, inside a carefully cooled flask in a cryogenics laboratory, there is a liquid that is partly here, in the ordinary sense, viscous and thermal and normal, and partly somewhere else, partly in a quantum state that is not a property of any one atom, but of all of them together. A collective state, a shared state, a state where the boundary between one particle and the next has, in a meaningful sense, dissolved. The helium atoms haven't disappeared, they haven't merged in any physical way. They still occupy space, they still repel each other when pushed together, they still have mass and charge structure and all of their individual physical properties. But their quantum identities have been pooled. They have, below 2.17 Kelvin, become something together that none of them is separately. A quantum object at human scale, that is what climbs your cup. And if you find yourself lying there in the dark, turning this over slowly, not quite believing it, well, that's the right response. It took the greatest theoretical physicists in the world, working across decades and continents, the creative leaps of Bose and Einstein in the 1920s, the hard experimental work of Kapitsa and Allen and Misner in 1938, and the mathematical architecture of Landau in 1941 to arrive at this picture. You are allowed to find it unbelievable. It is, by any ordinary measure, extraordinary, but it is not magic. It is physics, the specific, testable, measurable, reproducible physics of what happens when you take matter made of bosons and cool it far enough. The world does not break at 217 Kelvin. It reveals something, a layer of structure that was always there, always obeying the same laws, but that only becomes visible when the thermal noise is low enough to let the quantum nature of the atoms assert itself. Above the lambda point, the thermal energy is large enough to keep the atoms in their individual, separate, incoherent states. Each atom jostling and bumping and going its own way, the way atoms always go their own way in a liquid. The quantum nature is there, but it's hidden under the jostling. Below the lambda point, the thermal energy falls below the threshold at which the atoms can maintain their individual incoherence. And they condense, they share, the single wave function emerges, and the liquid, from the outside, looks exactly the same. Still a transparent, colorless cryogenic fluid sitting in a flask, except that it has stopped boiling, and the film has started climbing. And if you put your hand to its container, which you absolutely should not do because it is a couple of degrees above absolute zero, and contact would be instantly and severely damaging. But if you could sense it somehow, you would feel nothing unusual at all. The quantum revolution happening inside that cup makes no announcement. It simply happens. The boiling stops, the film climbs, the liquid sits there perfectly still, obeying physics more completely than anything you have ever seen. And somewhere nearby, in the laboratory, there is a porous plug and a small heater. And if someone turns that heater on, even slightly, with warmth no greater than the light of a flashlight, something happens that makes the two-fluid model feel not just elegant but genuinely startling. But that is the next part of our journey. We have arrived at the foundation, we have the model, and now the deeper truth beneath it. The superfluid component is the Bose-Einstein condensate, the quantum collective. The normal component is the rest, the thermal, individual, viscous fraction. They interpenetrate, they flow in opposite directions, they share a cup without sharing a nature, and the whole of helium-2's strange and beautiful behavior, the climbing film, the perfect heat conduction, the temperature waves called second sound that Vasilii Peshkov measured in 1944, all of it is derivable from this picture. Not by special cases, not by exceptions, not by saying the rules don't apply here, by applying the rules more completely than anywhere else in nature. The rules apply everywhere. In the Rollin film, creeping up a glass wall at 20 to 30 centimeters per second. In the second sound, oscillating back and forth through the bulk of the liquid, carrying heat as a wave. In the still surface of the flask where no bubble will ever form. In the lambda point itself, 2.1768 Kelvin, that precise, reproducible, invariant temperature where ordinary matter agrees, collectively and suddenly, to become something else. The rules all the way down, more completely than you could have expected, more beautifully than you had any right to hope. Lev Landau knew this. He worked it out in Moscow in 1941 with the war beginning around him, with the theoretical tools he had been building for years. He didn't see it as miraculous, he saw it as physics, which is perhaps the most extraordinary thing about physicists. They can look at something miraculous and say, yes, that is how it works, and mean it as a kind of love. He received his Nobel Prize in a hospital room. 21 years later, in 1962, the prize was for this picture of helium-2, for the phonons and the rotons and the two-fluid framework, for the mathematics of condensed matter that grew from this one cold liquid in a flask in Moscow. 21 years is a long time to wait for the world to catch up to an insight. But physics waits. The lambda point waits. The superfluid component goes on climbing its walls in the meantime, indifferent to human schedules, Indifferent to prizes and politics and the passage of years, it climbs because nothing stops it. It has been climbing since the first time anyone cooled helium-2 in a flask in the 1930s. It is climbing right now in cryogenics laboratories on several continents, in every carefully sealed vessel where helium-2 sits below 2.17 Kelvin, silently, patiently, at 20 to 30 centimeters per second. And the next thing it does, when someone brings a small source of warmth near the flask, is even more surprising. Imagine you are standing in a laboratory sometime in 1938. The room is cold, not the cold of a winter morning, but the cold of a place where real effort has gone into removing warmth from the world. There is a flask of helium-2 sitting on a bench, below 217 Kelvin, silent, glass smooth on its surface, and someone reaches toward it with a small lamp, not a powerful light, not a torch, not a heating element, not anything that would warm your hand from across the room, just a flashlight held near the flask, a faint, quiet warmth, the kind of warmth that would barely register against your skin if you held your palm toward it from a few centimeters away. The helium responds, not by warming slightly, not by gently expanding. It responds by spraying upward. A thin jet of liquid helium rises from the apparatus, a real, physical jet like a miniature fountain, driven upward by nothing more than the warmth of a light. No pump, no pressure difference, no moving parts, just warmth and a jet. John F. Allen and Harry Jones demonstrated this in 1938 in Cambridge, in the same year that Allen and Don Mizner had published their superfluidity result in Nature. They called it the fountain effect. Some people, encountering it for the first time, found it almost impossible to accept that what they were seeing was real. Heat causing liquid to spray upward. It violated every intuition about how heat and liquids were supposed to interact. And yet there it was. Reproducible, predictable, perfectly obedient to physics, just not the physics most people had in their heads. To understand why warmth creates a fountain, you need the two-fluid picture. You need to remember that helium-2 below the lambda point is not simply a cold liquid. It is two interpenetrating fluids at once, the normal component, which carries viscosity and entropy and the ordinary traffic of heat, and the superfluid component, which carries neither. Zero viscosity, zero entropy. A kind of fluid ghost that slips through the smallest gap, climbs any wall, and carries no warmth at all. Now imagine the porous plug. In Allen and Jones's apparatus, the flask of helium-2 was connected to a narrow tube packed with fine powder. A plug so densely packed that only the superfluid component, with its zero viscosity, could pass through it. The normal component, thick and viscous by comparison, was effectively blocked. The plug was, in a sense, a filter that passed only the ghost. And here is what happens when you introduce warmth near one side of that filter. Warmth in helium-2 is carried by the normal component. The superfluid component carries none. When you warm one side of the apparatus, you are enriching that side with normal component fluid. You are, in the language of the two-fluid model, converting superfluid fraction into normal fraction by adding entropy, by disturbing the quantum order. The superfluid fraction on the warm side decreases, and the system responds to that imbalance. The superfluid component from the cold side rushes through the porous plug toward the warm side, passing through the filter easily, frictionlessly, because it has no viscosity to impede it. It is trying to restore the balance. More superfluid arriving at the warm side. The normal component cannot escape back through the plug in the other direction because it is too viscous, too thick. So the fluid accumulates on the warm side. Pressure builds. And if the tube is open at the top, that pressure drives the liquid upward. A jet, a fountain. A spray of liquid helium rising into the cold air of the laboratory, driven by nothing but the redistribution of quantum order. The warmth of a flashlight, translated into the mathematics of quantum mechanics, translated into a fountain. There is something almost poetic about it if you let yourself sit with it for a moment. We think of warmth and cold as opposites. Warmth pushes, cold holds still. But in helium-2 the relationship is different and more intimate. The warmth is not forcing the liquid to flee. The warmth is creating an imbalance in the quantum population of the fluid, and the fluid is rushing to correct that imbalance through the only path open to it, and the rushing produces pressure, and the pressure produces the fountain. The warmth did not push the liquid. The warmth created a deficit of superfluid fraction, and the superfluid raced to fill it.
Nothing was pulling. Nothing was pushing in the ordinary sense. The system was simply restoring its own balance. And the restoration happened to look like a fountain?
Allen and Jones measured how high that fountain could reach. Under the right conditions, with a sufficiently high temperature gradient, still gentle by any ordinary standard, the fountain of helium-2 could rise tens of centimeters into the air. Thin, glittering in the laboratory light, impossibly real. A liquid climbing upward not because gravity had been defeated, but because the thermodynamic logic of the two-fluid state made climbing the only natural response. The fountain effect is formally called the thermomechanical effect. Thermo for the temperature difference that drives it, mechanical for the mechanical pressure, the real, measurable, physical pressure that results. Temperature becoming pressure, warmth becoming motion. In the ordinary world, these are not equivalent things. In helium-2, below the lambda point, they are coupled. They are two faces of the same quantum relationship. And there is an inverse. If the thermomechanical effect says warmth creates flow, the inverse says flow creates temperature difference. Force the superfluid through a narrow plug. Push it through mechanically using pressure. And something unexpected happens on the other side. The helium that has passed through the plug is colder than the helium left behind, and the helium left behind is warmer. This is the mechanocaloric effect. The name is almost charming in its literalness. Mechanical heat. Push fluid through a filter and you sort it thermally. One side warms, one side cools. No refrigeration cycle, no moving parts, no electricity required, just a pressure gradient and a porous plug and the strange quantum logic of a two-fluid state. The explanation is the same logic, run in reverse. When you force fluid through the plug mechanically, only the superfluid component passes through easily. The superfluid, remember, carries zero entropy, no heat at all. The helium that passes through is, in a sense, thermally stripped. It is the fraction of the fluid that carries no warmth. The helium left behind is correspondingly enriched in the normal component, the heat-carrying fraction. So the left-behind side warms and the pass-through side cools. You have sorted the fluid by its quantum nature, normal component on one side, superfluid component on the other, warmth on one side, cold on the other, achieved by nothing more than a push. If you find this beautiful, that is the appropriate response. It is beautiful. It is also, to a physicist, deeply satisfying because the mechanocaloric effect and the thermomechanical effect are not two separate phenomena. They are the same phenomenon, seen from two directions. Warmth produces flow, flow produces warmth. They are coupled by the two-fluid nature of helium-2, two faces of a single underlying quantum reality. Lev Landau derived them both from his model. He showed they were related by thermodynamic symmetry, that if one effect existed, the other had to exist as well by the internal logic of the physics. This is one of the things physicists love most, when a single framework predicts two things at once, and both turn out to be real. It is the universe confirming that the equations were asking the right question. And now let's set the fountain aside for a moment, though it is still spraying somewhere in your mind, and turn to what happens when superfluid helium moves in circles. Ordinary fluids rotate easily. Stir a cup of tea and the whole liquid wheels around, each part moving at a speed roughly proportional to how far it is from the center. The rotation is smooth, continuous, graded, fast at the rim, slower toward the middle, all of it connected in one seamless swirl. There is nothing quantized about it. The tea does not care about Planck's constant. Helium-2 cares. When you set superfluid helium rotating, by spinning the container, or by stirring, or by any other means, something very different happens. The fluid cannot rotate smoothly. The quantum nature of the superfluid component forbids it. Instead, the rotation concentrates into discrete, separate threads, thin whirlpools, each one a vortex line running through the fluid like an infinitely thin knitting needle of spinning liquid. These are called quantized vortices, and they are quantized in a very precise sense. Each vortex line carries exactly one quantum of circulation, not two quanta, not half a quantum. One. The quantum of circulation is h over m, where h is Planck's constant, and m is the mass of a helium-4 atom, a specific, fixed, universal amount. You cannot have a vortex line in superfluid helium that carries any other amount of rotation. If you spin the container a little, one vortex line appears, spin it faster and more appear, faster still, and they appear in greater numbers, organizing themselves into a regular lattice. Rows of spinning threads evenly spaced like a crystal made of rotation. The faster you spin, the more threads, but each thread carries the same fixed quantum of circulation. The total rotation of the fluid is not a continuous dial you can turn to any setting. It is a sum of discrete, identical units. This is quantum mechanics made visible at the scale of a laboratory container. Planck's constant is an extraordinarily small number. It governs the behavior of atoms and electrons. It has no business being visible to the naked eye or to any instrument observing the bulk behavior of a fluid you could hold in a cup. And yet in helium-2 below the lambda point, it is there. The discreteness is real. The vortex lines have been observed directly. Physicists have developed techniques to make them visible, to count them, to watch them move and interact and rearrange themselves under changing conditions. Each vortex line is, in a sense, a scar in the quantum wave function. The superfluid component is, as we have seen, a macroscopic, coherent quantum state. All the atoms sharing a single wave function, the way all the photons in a laser share a single, coherent light state. That wave function pervades the entire volume of the fluid. But rotation, in quantum mechanics, requires that the wave function wind around the vortex, phase by phase, in multiples of exactly one full turn. A fractional winding is forbidden by the mathematics. The wave function must come back to the same value after one trip around the vortex, and that requirement, that topological demand of the quantum state, is what fixes the quantum of circulation at exactly h over m, nothing more, nothing less. The vortex lattice is the superfluid's way of accommodating rotation while obeying quantum mechanics. It is a compromise between two demands. The container is spinning, but the quantum state refuses to spin smoothly. So the quantum state says, I will spin, but only in the way I am allowed to spin, only in units, only in discrete threads. The rest of the fluid, between the vortex lines, remains in its pristine, coherent state, flowing without friction, carrying no viscosity. It is a negotiation between the macroscopic world and the quantum world does not yield. Now consider what happens when the container stops spinning, or when the superfluid is simply set into circular motion and then left alone without the container to maintain the rotation. In an ordinary fluid, rotation decays. Viscosity dissipates the kinetic energy, the swirl slows. The fluid eventually comes to rest. This is what always happens in every liquid you have ever seen rotate: the bathwater, the stirred coffee, the river eddy. They all slow down. Given time, they all stop. In helium-2, the superfluid component has no viscosity. There is no friction to dissipate the kinetic energy. There is no internal resistance. The flow does not slow. If you create a persistent current in helium-2, a circular flow in a ring-shaped container like water flowing endlessly around a donut-shaped tube, and you keep the helium cold below the lambda point, that current continues. Not for seconds, not for hours, indefinitely, for as long as you maintain the temperature, for as long as the helium remains superfluid. The flow does not decay. It has been running since you started it. It will keep running frictionlessly because there is nothing to stop it. This is called persistent flow, and it is perhaps the most quietly astonishing property of superfluid helium. It is not dramatic. The way the fountain is dramatic, it does not spray upward or climb over walls. It simply continues steadily, silently. In a ring of metal in a cryogenics laboratory, a current of liquid helium circulates with no energy input, losing nothing, dissipating nothing, stopping for nothing. The atoms are not individual anymore in the sense that matters for friction. They are part of a coherent quantum state that spans the entire container. For friction to occur, for energy to be dissipated, the quantum state would have to be disrupted, broken, locally, in some way. But the coherent quantum state resists local disruption. It is topologically protected. Changing the flow state of the superfluid requires changing the macroscopic quantum configuration of the entire body of fluid, not just disturbing one atom or one small region. That requires an energy cost that is simply not available at the temperatures where helium-2 lives. So the state persists, the flow persists, the current runs on. There is an analogy to superconductivity, and it is not an accident. Superconducting currents also persist indefinitely in loops of metal cooled below their critical temperature. Electrons pairing up into a coherent quantum state, flowing without resistance for the same fundamental reason. A coherent quantum state resists the local disruptions that would cause dissipation. Kapitsa named superfluidity by analogy with superconductivity. The analogy goes all the way down to the mathematics. Both are macroscopic quantum phenomena. Both are examples of what happens when quantum mechanics reaches up to the human scale. In superconductors, the relevant particles are electrons. In superfluid helium-4, the relevant particles are helium-4 atoms. Which brings us to a brief digression. Brief, because this documentary belongs to helium-4, but necessary because the digression sharpens what is extraordinary about helium-4 specifically. Helium has a rarer isotope, helium-3, where helium-4 has 2 neutrons in its nucleus. Helium-3 has only 1. A lighter atom, heavier hydrogen but lighter helium-4. And this seemingly small difference in the nucleus changes everything about the quantum statistics of the atom. Helium-4 atoms are bosons. Their total spin, adding up the spins of the 2 protons, 2 neutrons and 2 electrons in each atom, comes out to an integer, 0. And bosons in quantum mechanics are allowed to stack. Multiple bosons can occupy the same quantum state simultaneously. In fact, they prefer to. Below a certain temperature, bosons rush into the lowest available quantum state, all of them at once, in a phase transition called Bose-Einstein condensation. This is the microscopic origin of superfluidity in helium-4. Helium-3 atoms are fermions. Their total spin is a half integer, 1/2. And fermions in quantum mechanics famously refused to share. No two identical fermions can occupy the same quantum state at the same time. This is the Pauli exclusion principle. It applies to electrons, which is why atoms have shells and chemistry is possible, and it applies to helium-3 atoms. They cannot condense one by one into a single shared quantum state, the way helium-4 atoms do. So helium-3 does not become superfluid at 2.17 Kelvin. At 217 Kelvin cooled in a laboratory, helium-3 is still a perfectly ordinary, slightly cold liquid. You can cool it further, well below the lambda point of helium-4, and it remains ordinary. You can cool it to 1/10 of a Kelvin, 100th of a Kelvin, and it remains ordinary. The Pauli exclusion principle stands guard. To become superfluid, helium-3 needs a different mechanism entirely. The atoms cannot condense individually, so they must pair up. Two helium-3 atoms with their half-integer spins form a pair with an integer total spin. A pair of fermions is a boson, and bosons can condense. This is precisely what happens in superconductors. Electrons, which are fermions, pair up into Cooper pairs, which are bosons, and those pairs condense into a superconducting state. Helium-3 does the same thing with atoms instead of electrons, but the pairing requires extraordinarily low temperatures. The transition temperature for helium-3 superfluidity is around 0.025 Kelvin, 2.5 thousandths of a degree above absolute zero. A temperature so cold it makes 2.17 Kelvin look almost balmy. This discovery was made in 1972 by Douglas Lee, Douglas Osheroff, and Robert Richardson, working at Cornell University. They received the Nobel Prize in Physics in 1996 for it. The contrast is illuminating. Helium-4 with its bosonic atoms becomes superfluid at the relatively accessible temperature of 2.17 Kelvin, accessible enough that Pyotr Kapitsa could achieve it in his Moscow laboratory in the 1930s with the equipment of that era. Helium-3 with its fermionic atoms required a completely different physics and temperatures 3 orders of magnitude colder, temperatures that were not routinely achievable until decades later, with refrigeration technology far beyond what Kapitsa had available. The boson nature of helium-4 is not a minor detail, it is the whole story. It is why the self-emptying cup exists. It is why the fountain sprays. It is why the flow never stops. Helium-4 is superfluid at 2.17 Kelvin because its atoms are bosons, because bosons condense, because Bose-Einstein condensation produces a macroscopic quantum state, and because a macroscopic quantum state has no friction. Helium-3 tells the same story in a harder key. It required colder temperatures, different physics, a later generation of scientists with better tools, but it arrived at the same destination, a superfluid, a state without friction. The quantum world reaching up and making itself visible in a flask, both are extraordinary. But helium-4 came first, and helium-4 is the liquid that climbs out of its container, and helium-4 is the reason we are here tonight. Now, a note about Pyotr Kapitsa, because the story of superfluidity is also quietly the story of a man. Kapitsa was a Soviet physicist who spent the better part of a decade at the Cavendish Laboratory in Cambridge, in England, working under Ernest Rutherford, one of the great physicists of the early 20th century, the man who discovered the atomic nucleus. Kapitsa was brilliant, and Rutherford recognized it. He built a magnetic laboratory for Kapitsa at Cambridge. They worked together well. Kapitsa had a life in England, colleagues, friends, a reputation, equipment. In 1934, he went home to the Soviet Union to visit his family. He had done this before. It was a normal thing. He planned to return to Cambridge, as he always had. He was not allowed to return. The Soviet government detained him. He was told he would be continuing his work in the Soviet Union. this was not presented as a choice. The political situation of the 1930s, Stalin's consolidation of power, the growing restrictions on the movement of Soviet scientists, had closed the door behind him. He was trapped. Rutherford in Cambridge faced a difficult situation. He had Kapitsa's laboratory equipment, the machinery and apparatus that Kapitsa had spent years acquiring and using. The Soviet government wanted it. Rutherford negotiated. Eventually, the Soviet Union purchased Kapitsa's equipment and had it shipped to Moscow so that Kapitsa could continue his research in his new, involuntary home. This is the laboratory where superfluidity was discovered. Equipment that had been in Cambridge purchased and shipped to Moscow, set up in a new institute used by a physicist who had not chosen to be there. The discovery came in 1938. Kapitsa published in Nature, the same journal, the same issue, the same week as Allen and Misner in Cambridge. Two groups on opposite sides of a Europe that was lurching toward war, arriving at the same threshold simultaneously. The name Kapitsa chose for the phenomenon, superfluidity, is the name we use today. He did not receive the Nobel Prize in 1938. He did not receive it in 1941 when Landau's theory explained what he had found. He did not receive it in 1944 when Peshkov confirmed second sound. He did not receive it through the 1950s or the 1960s or most of the 1970s. The prize committee moved slowly. History moved the way history moves. Pyotr Kapitsa received the Nobel Prize in Physics in 1978. He was 84 years old. The work had been done 40 years earlier in a laboratory he had not chosen to be in a city he had not chosen to stay in, discovering a phenomenon that the world would spend decades learning to understand. He died in 1984, 6 years after the prize. He had lived long enough to be formally recognized. That is more than some physicists manage. There is something in this that is worth holding gently for a moment, here in the quiet. The science did not care about the politics. The lambda point did not move because Kapitsa was detained. The superfluid component climbed its walls in the Moscow flask, just as it would have climbed them in the Cambridge flask. The physics was indifferent to borders and politics and the decisions of governments. And yet a human life was changed by all of those things, shaped, redirected, confined. And from that confinement came a discovery that opened a new chapter in our understanding of matter. It is not a comfortable story, it is not a triumphant story in a clean sense, but it is the story of how superfluidity was found. And it is worth knowing because the science did not emerge from a vacuum. It emerged from a life. Now let us turn gently toward the close of this night's journey. We have been descending through temperature since the beginning, from the ordinary world where liquids flow and freeze and boil in the ways we expect, down through the colder regions that Kamerlingh Onnes first reached in 1908 in Leiden, down to 4.2 Kelvin, where helium finally becomes a liquid. And then further down, past 4.2, through the boiling, vigorous and ordinary, through the long, cold descent to 217 Kelvin, where the boiling stopped and the liquid went silent. And below that threshold, in helium-2, we found a new state of matter, a state that flows without friction, that climbs walls in a film 30 nanometers thick, that sprays upward when warmed, that circulates forever when set spinning, that conducts heat hundreds of times better than copper, that carries temperature waves instead of heat through diffusion, that organizes its rotation into quantized threads, each one carrying exactly 1 unit of Planck's constant divided by the mass of a helium atom. All of it, every uncanny behavior, descends from one fact. Below 2.17 Kelvin, the helium-4 atoms, which are bosons, which carry integer spin, which can and do share quantum states, begin to condense into a single, shared quantum ground state, a macroscopic wave function, an object described by quantum mechanics that is the size of a cup. And a macroscopic quantum state has no friction because friction requires disruption of the state, and disrupting the state of the whole fluid would cost more energy than is available. The friction does not decrease gradually. It does not thin out as the temperature drops. It vanishes. At the lambda point, it vanishes. And everything else, the climbing, the spraying, the eternal circulation, is a consequence of that vanishing. The liquid does not climb because something pulls it up. Nothing pulls it up. Gravity is still there, doing exactly what gravity always does. The liquid climbs because nothing stops it. The film creeps up the wall because the wall offers no resistance. Every surface is a path, and every path is equally open because there is no friction to distinguish a horizontal path from a vertical one. The concept of effort, in the ordinary sense, has ceased to apply. It is a strange kind of freedom. Not the freedom of something powerful overcoming resistance. The freedom of something for which resistance has simply ceased to exist. We sometimes describe superfluid helium as defying gravity or defying physics or as a liquid that nature somehow got wrong. These are descriptions that belong to our surprise, not to the helium. The helium is not surprised. The helium is not defying anything. The helium is doing exactly what the equations say it should do, at exactly the temperature the equations predict, in exactly the way Landau worked out at his desk in Moscow in 1941, with the war going on outside his window. The helium is obeying physics. It is obeying physics so completely, so cleanly, so without any of the thermal noise and imperfection that characterize the warmer world, that the physics becomes visible. The quantum nature of matter, which is always there, which governs everything, which underlies all of chemistry and all of material reality, is usually hidden beneath layer upon layer of thermal agitation, of atoms jostling and colliding and disturbing each other's quantum states. At room temperature, the quantum world is present but buried. You need careful experiments to see it at all. At 217 Kelvin in helium-2 it surfaces. The thermal noise quiets, the atomic jostling settles. The quantum coherence, which was always waiting underneath, emerges to the surface and takes over. The single quantum state spreads across the entire volume of the fluid, and the result is a liquid that climbs out of its container. This is not magic, it is not a violation. It is, if anything, the opposite, is physics, at its most honest, its most pure, revealed to us by the simplest possible atom, helium, which has no chemistry to complicate it, no bonding to interfere, no structural ambitions, just 2 protons, 2 neutrons, 2 electrons, just enough complexity to be a boson, simple enough to show us what bosons do when the world gets cold enough. What the superfluid shows us is that friction is not fundamental. It is not a law. It is a property of the warm, noisy world we happen to live in. A world where quantum coherence is constantly being scrambled by thermal energy. Remove enough of that energy and the friction goes with it. What remains is the quantum reality underneath, frictionless, eternal, climbing. And here is the thing about that, the thing worth carrying into sleep. You are warm. You are made of atoms that are constantly jostling, constantly colliding, living in a world far above 217 Kelvin, far above any temperature where quantum coherence governs your bulk behavior. The quantum world is present in you, and it underlies your chemistry, your molecular bonds, every reaction in every cell. But it is hidden, overlaid by warmth and complexity and the beautiful mess of a living system. But it is there. Beneath the thermal noise, beneath the molecular traffic, beneath all the warm business of being a biological thing, the quantum nature of the atoms that make you up is exactly the same as the quantum nature of the helium atoms in that flask in Moscow. You are made of bosons and fermions too. You are governed by the same Planck's constant, the same quantum statistics, the same deep rules that produce quantized vortex lines in a rotating cup of helium. The superfluid is not alien to you. It is a glimpse of what the world looks like when it is stripped down, cooled down, quieted to the point where the underlying order becomes visible. It is the universe showing you its skeleton. And the skeleton is beautiful. Kamerlingh Onnes stood in his laboratory in Leiden on the 10th of July 1908 and watched liquid helium collect in a vessel for the first time. He reached 4.2 Kelvin, a temperature that required years of effort, careful engineering, a new kind of refrigeration built specifically for this purpose. He was the first human being to see liquid helium. He did not know then what waited 30 years down the road. He did not know about the lambda point, or the two-fluid model, or the Rollin film creeping silently up the walls of the flask. He was just cold enough to see the liquid, and that was, for that moment, extraordinary enough. The lambda point waited. The superfluid waited. The film was already climbing, in principle, in the physics that governed the atoms in front of him, in the mathematics that Landau would not write down for another 33 years. It was all there, hidden in the helium, waiting for the temperature to fall a little further. We have spent this night following the temperature down, through the boiling, past 4.2 Kelvin, down toward the silence at 217. We have watched the liquid transform. Helium, I becoming helium-2, the ordinary becoming extraordinary. We have seen the film creep over the walls. We have watched the fountain spray upward from the warmth of a flashlight. We have heard, in a sense, the second sound moving through the fluid like a temperature wave. We have seen the vortex lines arrange themselves in their quiet lattice, each one carrying its exact quantum of circulation, no more and no less, because the universe does not negotiate with Planck's constant. And we have arrived at the place where all of it makes sense, not the sense of being familiar or ordinary or unsurprising, the other sense, the sense of being consistent, of following from the rules, of being, at its deepest level, a consequence of the quantum nature of matter applied to a cold enough place. The liquid climbs because nothing stops it. The fountain sprays because warmth creates an imbalance in the quantum population, and the system rushes to restore the balance, and the rushing makes pressure, and the pressure makes a jet. The flow persists because a coherent quantum state resists disruption, and there is not enough energy available below the lambda point to disrupt it. Every mystery, the same cause, the same threshold, the same vanishing of friction at 2.17 Kelvin, one transformation, seen from many angles. Pyotr Kapitsa named it superfluidity. Lev Landau explained it. John Allen and Don Misner measured it, and Allen and Harry Jones made it spray. Vasilii Peshkov listened for the temperature wave and heard it. Kamerlingh Onnes opened the door in Leiden in 1908 without knowing what lay on the other side, and now you know. Not because you need to know it for anything in particular, not because you will use this information tomorrow in some practical way, but because the world is stranger and more beautiful and more precisely logical than it appeared before you knew it. Because somewhere in a cryogenics laboratory on several continents, there is a flask of helium-2 sitting below 17 Kelvin, and a film 30 nanometers thick is climbing its walls right now, silently, patiently, at 20 to 30 centimeters per second, because nothing stops it. And that is a true thing about the world you live in. Wherever you are listening from tonight, whatever time it is in your corner of this strange, quantum-governed planet, whether you have a lamp on or a window open or a blanket pulled up, whether the room is dark or the city is still glowing outside, you are made of the same stuff as that helium. Your atoms are obeying the same rules. The quantum world is present in you, quiet and exact, covered over by the beautiful warm noise of being alive. The flask of helium-2 shows you what the quiet looks like, what the warmth is covering, the clean, frictionless order underneath all of this. That, I think, is something worth drifting towards sleep with. Not the strangeness of it, though it is strange. The order of it. The way the universe, cooled to the edge of the coldest that can exist, reveals itself to be not chaotic at its foundation, but precise, quantized, coherent. The same quantum of circulation every time. The same threshold, 17 Kelvin every time. The same 30 nanometers every time. The universe is not making it up as it goes. It knows exactly what it is doing. It has always known. If you enjoyed this slow journey through the cold, a gentle like or subscribe means a great deal. Small creators like me rely on your support to keep these nights going. And if you'd like to tell me where in the world you are listening from tonight, and what time it is in your corner of the dark, I would love to know. That small thing, knowing where you are, knowing these words found you, is one of the better parts of making something like this. To those of you already here, already subscribed, already part of this quiet little community of curious late-night wanderers, thank you. It is a genuinely lovely thing to have company on these journeys. Sleep well, fellow voyager. The next journey keeps until you wake.